Xupeng Miao and Gabriele Oliaro. And Xupeng is a postdoc at CMU working with Professor Zhihao and Professor Cheng. And he was recognized with the 2022 ACM China Doctoral Dissertation Award. And in this talk, he's going to talk about a tree-based speculative inference and verification system to accelerating LLMs. So this talk will be given by the two speakers. So with that, you can take it over.
Okay. Thanks for the introduction. Hello, everyone. I'm Xupeng Miao from Carnegie Mellon University. Welcome to our talk about SpecInfer, the first tree-based speculative inference engine for large language models. This work was finished by members from Catalyst Group from Carnegie Mellon University, as well as our colleagues from Tsinghua, Stanford, SGTU, Peking University, and UCSD. Generative language models like ChatGPT have demonstrated remarkable progress on various domains, such as chatbot, code generation, and task automation. However, it's challenging to cheaply and quickly serve these language models due to their large volume of parameters, complex architectures, and high computational requirements. For example, we need at least 10 A100 GPUs to serve a single 175 billion GPT-3 model in high precision. It takes 0 seconds to serve a single inference request. For example, generating 256 output tokens needs around 20 seconds. To avoid recomputing keys and values during attention calculation in large language models, existing serving systems generally catch the keys and values of all tokens for reuse in future decoding iterations, which may also consume gigabytes of GPU memory. Recently, the competition between different language model API providers is very fierce in terms of their serving system efficiency. This figure shows the response time of 100 tokens within a single inference request for different models. In this talk, we will show that the main performance bottleneck of existing large language model serving system comes from the incremental decoding algorithm, where each decoding step only generates a single output token, using the input prompt and all previously generated tokens. During each step's calculation, most operators will be the product between a small token vector and the model weight matrix. With such a fine-grained GPU kernel execution mechanism, it's hard to fully utilize GPU compute resources. On the other hand, incremental decoding also requires to access all model parameters and the key-value cache to decode even a single output token, which makes the decoding process highly memory-bounded. There is an important observation worth to be mentioned. Existing public language models are usually released with several variants in different scales. For example, the smallest GPT-3 model only has 125 million model parameters. It shows pretty low model performance on different text generation tasks, but it can be hundreds times faster than the largest 175 billion model. Considering these factors, we are going to ask the following question. Is that possible to achieve the best of both from small model and large model? We want to build a cheap, fast, and accurate serving system. A promising alternative solution is called speculative inference, or speculative decoding, which was first proposed by Google and DeepMind individually. They are also called sequence-based speculative inference. It involves an additional small model as the speculator. The small model is responsible for taking a quick guess on the next few output tokens. The speculation can accelerate the decoding process, but we also need to guarantee that the speculated results will not change the original language model outputs. So existing approaches really use the original language model to verify the speculated token sequence and correct the wrong predictions. Then the verified results will be sent back to the speculator and continue the iterative decoding process until all the output tokens are generated correctly. However, this approach is difficult to achieve significant speedups in real-world applications due to several practical challenges. There are mainly three parts. The first is The speculation of small model should be very fast. Due to the data dependency during the speculative decoding process, the speculation will block the verification process because it should be finished in time. Ideally, we want a speculator which may have nearly zero time cost. Second, the verification step should also be efficient. It may not be as efficient as small model execution, but it cannot be worse than incremental approach. For example, if you want to verify 3 tokens, it should be faster than 3 steps of the original decoding process. Third, the speculation should also be accurate, which means the small model's output should align well with large model. In an extreme case, the small model always generates wrong predictions. Then at each verification step, the large language model can only output the next correct token, which stagnates to the incremental decoding approach. Now I will hand over to Gabriele to introduce our solution.
To address this practical challenge, we propose SpecInfer, our tree-based speculative inference and verification solution. SpecInfer consists of 2 key techniques: a learning-based speculator, which generates speculative tokens fast and accurately, and then a tree-based verifier, which verifies the token's correctness efficiently. The basic workflow of SpecInfer works as follows. So first, the speculator takes a sequence of tokens as input, but unlike the previous approaches where the speculator outputs a sequence of tokens, here we produce a speculated token tree. A sequence is actually also a special case of the tree, but the goal here is to maximize the overlap between the predicted token and the LLM's original output, and we found that a tree works better for this goal. We support 2 different methods to generate the tree of speculated tokens. One is merge-based token tree construction, which relies on multiple diverse SSMs and merge their predictions. Our experiments have observed larger and larger speedups when we involve more small models in this process. Another method is expansion-based token tree construction, which uses a single SSM together with decoding methods such as top K sampling to track multiple prediction branches. As you can see, when we increase the tree size by increasing K from 1 to 5, which means we select up to the top 5 candidate tokens from the small model's output distribution to then verify, we can achieve a nearly 96% acceptance rate for the next token prediction. The second component of SpecInfer is the verifier. The verifier takes a speculated token tree from the speculator, it flattens it, and then uses the LLM to verify the tokens against the LLM output. To do so, we introduce a novel tree-based parallel decoding algorithm and an efficient kernel implementation to simultaneously verify all tokens from a token tree in a single LLM decoding step. So to verify a tree of speculated tokens using existing solution, we will need to iterate through each branch of the tree and compute the attention independently. So to prevent the branches of the tree from interfering, we have 2 options. Either we can process them sequentially and let them write to the same KV cache, or we can process them in parallel, but we need to use separate KV caches. So the issue of these approaches is that the first approach will do redundant computation and also result in GPU underutilization, whereas the second approach introduces a large memory overhead. So to do this more efficiently, we introduce a new operator, which we call tree attention. Tree attention takes a tree of speculated tokens as input and produces an output that is equivalent to running attention on each branch of the tree independently. But tree attention does this using a single forward pass, using all the computation from the branches together. There are 2 key optimizations here that makes this approach possible. First of all, we have a DFS-based approach such as, for example, in order traversal of the tree, to linearize the tree into a flat sequence. And then we use a topology-aware causal mask, which ensures that for each token, the only attention scores that are considered are those corresponding to tokens from the same branch of the tree. These are exactly the only tokens that have a causal relationship to the tokens being considered. So after applying this mask, we can run the attention operator in a single forward pass. And this prevents any redundant computation and memory consumptions. Our experiments use 3 public available dataset of prompts to benchmark the performance of our system, and we can show that SpecInfer outperforms the state-of-the-art by up to 3 times. In these slides, we will show 3 different scenarios. So first, we run an experiment on a single GPU with Llama 7B as the model. Then we run another experiment with still a single node, but multiple GPUs using OPT 30 billion model. And then finally, we run an experiment on a multi-node scenario. So we use 2 nodes, each with 4 GPUs. And whenever we use more than 1 GPU, we use tensor model parallelism to parallelize within the same node, and pipeline parallelism to parallelize across nodes. So first, we benchmark alternative solutions, existing systems such as VLLM, Eigenphase, and Facet Transform. And for the multi-node case, we actually only show the numbers for Facet Transformer because VLLM and Eigenphase don't support this scenario yet. And then we will conduct an ablation study. So we measure the performance of our runtime, which is the pink bar in this slide, and compared to the baseline, and we show that our runtime is equivalent or sometimes even a bit slightly slower than the baseline. But then we turn on sequence-based speculative inference, which is the light orange bar, and we can immediately see a speed up across all scenarios. And then finally, when we enable our solution, which is tree-based speculative inference, the dark orange bar here, we can see a significantly lower latency than all other solutions across all scenarios. So we first released our paper preprint in May 2023, and we open source our code as part of the FlexFlow repository on GitHub. The repository has now been starred over 1,500 times, and tree-based speculative decoding method has been widely adopted by follow-up work since our initial release, with more than 40 tree-based speculative decoding papers since the first release of our paper. Thank you very much for listening, and we are open to any questions for the audience.
Any questions?
Yeah, I can just talk about it. Are there any, like, for the small model and using Speculative, are there any modeling side changes that we'd be interested in making so that this works better? Like, for example, maybe we could like increase the temperature on the inference so that you cover a wider range of possible sequences so the verifier can find a good sequence.
I think that's a really good question, actually. So that's something that is a bit orthogonal to our work. But yeah, there's definitely many possible follow-up possible. So combining that with like multiple settings, such as temperature setting, is definitely something that can be added on top of the system and improve the performance. Another possible future work is, for example, using different tree sizes and 3 dimension based on the specific prompt and specific sentence. So yeah, this is definitely something that it's interesting to look into.
Any other questions?
Just one add on from Wang. It's kind of like a correctness question, because you showed that you're getting 2.3x speed up, and I think that's great. But what about the output? Did you get the exact same output as the reference, or were there any let's say anomalies that would be interesting?
Right. So whenever we do speculative inference, there's 2 ways to do it. One is in a lossy fashion, where the output is supposed to be very similar, but not necessarily always identical to incremental decoding. And then you can do it in a lossless fashion, in which case you're guaranteeing that the output is always the same. And so there's a trade-off between these two approaches. And we ended up picking the lossless fashion. So our output is guaranteed to be always the same as incremental decoding.
All right.
What is the overhead of your approach in terms of resources needed and energy consumption that is increased beyond the baseline?
So in our approach, our small speculative models are usually about 100 times smaller than the LLM. And so like the overhead of running the small speculative models is negligible because it's just so much more than the LLM. And so our approach actually takes advantage of GPU underutilization. So we run it whenever the GPU would otherwise be underutilized. So in this sense, we don't have any significant additional overhead. We just use resources that otherwise would not be, would stay idle. But yeah, if you use a small speculative model that is too large, then you add some overhead. So it becomes counterproductive.
All right. I think rest of the questions you can take it offline. So let's thank the speaker once again. So the next talk is given by two speakers again. First speaker is going to be Jiao. He's an associate professor at Nanyang University, and Zhang is a PhD student at the same university. They'll be talking about XCGPT, a constraint-aware resource scheduling for LLM inference systems.
Okay, thank you. Again, I'm Jiwon. I'll be presenting our work at XGPT with my PhD student, Hyungjun here. LLM inference is challenging due to their large size and irregular executions. Because of their size, parallel execution on multiple GPUs is required, and it is hard to select the optimal parallel setting. Also, LLMs run by encoding all input tokens once, and then decoding a token at a time auto-regressively. So encoding and decoding has very different amount of work. Moreover, it is hard to predict the query's output sequence length, which also complicates the execution. So let me visualize these problems in this timeline. It shows LLM inference on two GPUs in a pipeline parallel manner. At the top, faster transformer or FT runs encoding in 2 micro batches in blue, and then it runs decoding in orange until all the queries in the batches complete. And then it runs the next batches. So as decoding proceeds, the batch size decreases, which reduces the inference throughput. So to mitigate this problem, in Orca, encoding of new queries replace completed queries in a batch, and this encoding runs together with decoding of previous queries. And this keeps decoding batches to be sufficiently large. However, because encoding and decoding has different amount of work, it induces pipeline bubbles like this. So that was the problem number 1 in LLM inference. Performance problem due to decreasing the batch size and pipeline bubbles. The second problem is that in these systems, to improve latency, you have to run with smaller batches, which could sometimes substantially degrade the throughput. We propose XGPT, which is the system that optimizes LLM inference with efficient throughput latency trade-off. It finds an optimal parallel setting that maximizes throughput, satisfying a given latency constraint. It consists of the profiler, simulator, scheduler, and runner. The profiler measures the execution times of a single encoding and decoding layer with all possible parallel settings, and the result is used by the simulator to construct an execution timeline when requested by the scheduler, which finds the optimal schedule. XGPT supports 2 allocation policies, round-robin and workload-aware allocation, or RA and WA policies. In RA, we simply and evenly distribute the encoders and decoders across all GPUs. distributing encoders and then decoders in the same manner. For decoder-only models, we only distribute decoders, of course. In WA, however, we dedicate GPUs to either encoding or decoding. In doing so, we make each GPU to have equal amount of execution time. So for example, if encoders takes twice the execution time of decoders, then we assign layers like this so that each GPU has equal execution time. For decoder-only models, WA stores 2 copies of the model, one for encoding and another for decoding. So we'll get back to this memory overhead later. Now, scheduling for those allocation policies. First, for RA, we run encoding in all GPUs like this. And then in decoding phase, we decode only for a fixed number of iterations and the number of iterations. And then we encode a new batch, after which we combine new and previous batches and encode them together. And this is repeated. So this way, RA scheduling can maintain sufficiently large batch without causing too many pipeline bubbles. Still, we have small bubbles between encoding and decoding phase. So RA puts more emphasis on keeping large batch size than reducing pipeline bubbles. In this scheme, we can control the throughput and latency using the encoder batch size or the number of decoding iterations. For example, if we increase ND and run encoding more frequently, then with larger batch size, throughput improves, but latency decreases for running many other queries encoding. Now in WA, GPUs are dedicated to either encoding or decoding. So the encoding GPUs execute encoding of new queries in every iteration like this, while the decoding GPUs compute with the encoded queries, generate a single token, and then combines the new and previous queries and decode them together to generate the next token, and so on and so forth. Recall that WA has the memory overhead for decode-only models because it stores 2 copies of the model, right? So with this memory overhead, WA runs with smaller batches than RA, but it minimizes pipeline bubble better than RA. For small LLMs, this strategy works well, as we'll see in later slides. In this scheme, we can control the throughput and latency trade-off using encoder batch size, the number of decoder microbatch, or partial tensor parallelism. So, for example, when we apply decoder microbatch and shrink the decoder stages like this, then the latency to generate each token reduces, but the throughput declines with smaller batch size. Moreover, XGPT applies tensor parallelism to a subset of GPUs as a means of controlling throughput and latency trade-off. So here, TP is applied to the last 2 GPUs, reducing the number of pipeline stages to 3. So this improves the latency, but degrades throughput due to the synchronization overhead between tensor parallel GPUs. So with these control variables, we aim to find their optimal values that maximize throughput, satisfying the latency constraints. In doing so, we exploit the input and output sequence length distribution, PE and PD, which we can obtain by observing NMP services. To find a solution, we take advantage of the monotonicity property of the control variables. So that is, the throughput and latency functions are monotonic to each control variable. So for example, if we fix other control variables as constant and increase the encoding batch size, then throughput always improves, latency always degrades. Actually, we intentionally design the control variables to be this way so that we can formulate a standard monotonic optimization problem. So we designed an optimization algorithm based on the standard branch and bound method. The algorithm for 2 control variables, x1 and x2, proceed in these steps, dividing the search space, updating the optimum throughput, and pruning with monotonicity property. So this process is pretty much standard. So please read the paper for the details. So now Hyungjin will present the rest.
So our simulator constructs the execution timeline using the profiling result. For the timeline simulation, we need to consider these 2 things. First, for RA scheduler, we set the encoding batch size to be the same as the number of completed queries in ND decoding iterations, so that the batch size is consistent across the execution. Second, for the accurate simulation, we need to calculate the expected batch size of each encoding decoding iteration. And for that, we must consider the margin of batches after each encoding phase. In other words, we need PDU, the probability that a query completes at U decoding iteration. We can compute PDU if we have PDS, the output ranks distribution. PDU is derived from PDU given S, the probability when the ranks is given. Let's consider when ND is 3 and S is 5. Then what is the probability that this query completes at U is 2? At this decoding iteration, the sequence S has 1 out of 2 chance to complete at U is 2 because it may have started in the current or previous encoding iteration. So there are S divided by ND, number of starting points, and the probability is computed like this. And I don't have time to get into details, but generally PDU given S and PDU is computed like this. XGPT runner is based on FT, and we implemented these optimizations. I will briefly explain the last one, how we transfer KB cache in WA. In WA, we need to transfer the KB cache from encoding GPUs to decoding GPUs. If we naively perform the transfer like A, the overhead affects the performance. So we optimize the transfer like B to improve the performance. We evaluated XGPT with other systems using 6 models and 2 GPU clusters. As FT executes faster than other systems, we mainly compare XGPT to FT. We evaluated with 5 NLP tasks, and for each, we synthesize a dataset as shown here. We evaluate with each task using 4 latency bounds, including infinity. For small LLMs, we evaluate with S, T, and C, as these tasks typically execute on small LLMs. Across all experiments, XGPT is on average 2 times faster than FT and maximum 5 times faster. For these relatively small LLMs, WA in blue can perform better than RA in orange in many settings, even with its memory overhead. For large LLMs, we evaluate with G, C1, and C2, as these tasks typically require large LLMs. We evaluate only RA scheduling, as the memory overhead of WA is critical for these large LLMs. In all experiments, XGPT is 3 times faster than FT and up to 15 times faster. Recall that WA stores 2 copies of a decoder-only model, and we measured this memory overhead. You can see that WA consumes more memory for the model parameters than FT, shown in the blue bar. Also, as we assign GPUs based on the encoder-decoder execution times, the memory consumption is imbalanced. Still, we achieve better throughput when consuming the same amount of memory in total. Let's say the distribution changed after we fix schedule. Then if we want to solve without rescheduling, we need 10 to 20% safety margin when the average or variance changes. When this case 1 here, or if we want to reschedule, the overhead is less than 10 seconds in XGPT, which is case 2 here. We validated the experimental result with 3 real-world datasets, CNN, WMT, and ALPCA. The details are in the paper, but the results are similar with XGPT 4 times faster than FT. To summarize, we proposed XGPT for optimizing LLM inference. XGPT supports 2 allocation policies, each with 3 control variables. We demonstrate that XGPT largely improved the throughput and latency. Thank you, and we are ready to take questions.
All right, any questions? Right, I had one question. So can you give some intuition as to why the monotonicity property will hold, like when you have like interaction between control variables? Like
So the throughput and latency is monotone to each of the control variables. So when one control variable, all the other control variables are fixed, then increasing or decreasing one control variable resulting in better or worse throughput or latency. So there's no interaction between different control variables.
So have you tried any machine learning model to solve the optimization
finding
problem?
No, but maybe but we haven't tried that path yet.
Okay.
Yeah.
Any questions from the audience?
Yes, so the question I have is that my understanding of your Wang approach is similar to this desegregation.
Similar to
some recent work of desegregating prefitting and decoding. Essentially, you run prefitting specifically on one cluster, and then you transfer TD cache
right.
to another cluster.
So is that the work by Microsoft?
Yeah, I think Microsoft has Splitwise, and I think UCSD has another work about these LM. On this server.
Right.
So I'm curious to know what's the difference between your Wang approach and this recent work, and do you think this separation or the segregation approach is the future way for serving? Because there is also, as you said, there is a redundancy in terms of weights, in terms of replicating the model weights.
Right. First of all, our work was, submitted to the summer cycle, and it was like affected.
Before this.
So that's one. And another is, well, one big difference is like ours also considers like the latency constraint and controls the throughput and latency to sort of maximize throughput under given latency constraint. And our experience with Wang is that it works pretty well for small LLMs where your memory overhead matters less than really large LLMs. So it works pretty well for small LLMs, as you see in this the experimental result with small LLMs. But we couldn't run Wang for really large LLMs because of their memory overhead. So I think probably for small LLMs, but these days there are a lot of small LLMs ranging from 5 to 10 billion parameters. So for those, I think it's going to work pretty well.
All right, let's thank the speakers again. So our third talk is given by Shoaib. He's a final year student working on systems of machine learning, and he's graduating in fall and he's looking for research positions in the industry. And his paper proposes a Proteus, a system for ML inference on resource-constrained compute clusters.
Hello, everyone. So my name is Shoaib. Thank you for the introduction, and I'm going to present Proteus, a high-throughput inference serving system with accuracy scaling. So before we go into the details of Proteus, let's talk about the life cycle of machine learning models, which typically looks like this. In the first phase, the model is developed, which consists of things like defining the model layers and parameters, feature engineering, data collection, and so on. The model is then trained, which may take several hours to days or even weeks, followed by fine-tuning, which prepares the model for production. And then finally, the model gets deployed to serve inference requests for users, where it spends most of its life. In fact, Meta recently reported expanding their infrastructure capacity by 2.5x to meet the inference demand, and NVIDIA reported that inference is estimated to take about 80 to 90% of the total cost of ML. In this paper, we present an inference serving system that focuses on this phase of the model lifecycle. Now, an inference serving system is a service maintained by a cloud provider that may have a number of servers, and the service can host a machine learning model so that when a client needs to run an inference, they can send an inference request to the provider, who will run the request on one of the models hosted on their servers and return the response. An inference serving system may host one or many applications, and these applications may have different requirements in terms of things like how fast the user wants a response or how accurate they want the response to be. The provider wants to maximize their throughput so they can serve as many requests as possible using their available resources in order to make the maximum profit. As the provider tries to serve machine learning models, the demand for these models actually changes throughout the day. For example, there may be a higher demand during morning or noon hours, which we call peak hours, and lower demand during the night, which we call the off-peak hours. As the demand changes throughout the day, these existing systems typically respond by scaling the hardware resources to meet the demand. For example, when the demand is high, the system may scale up the number of servers to meet the demand. And when the demand returns to normal during the off-peak hours, the system may scale down by removing the additional servers. We call this existing approach hardware scaling, and this approach actually has several limitations. First of all, adding more servers can be expensive And secondly, it may not even be feasible for small clusters owned by enterprises or edge clusters due to the limited availability of hardware resources. If the provider cannot allocate enough resources to meet the increased demand, it may result in delayed responses for users or even drop requests. In this paper, we present an alternative approach to hardware scaling, and this approach is based on the fact that an ML model can have multiple variants, which are essentially different versions of the same model that offer different points on the throughput versus accuracy trade-off. These models can be generated by the model developer, such as in the case of efficient net variants, or for example, ResNet, or they can be generated after training through mechanisms such as model compression, quantization, pruning, and so on. So when the demand is high, using a higher accuracy model variant, using a lower accuracy model variant can provide a higher throughput and serve more requests using the same hardware resources. And when the demand is low, we can move back to higher accuracy model variants to ensure high quality of service. So we call this approach accuracy scaling, and it is particularly useful for applications where a timely response is more critical than an accurate but sluggish response, or worse, a drop request. So even though accuracy scaling is a promising direction, it actually has several challenges. First of all, we need to accommodate the variations in query loads at multiple timescales. For example, we may see the macro scale variations over minutes or hours of the day that I just showed you, but we may also have variations at the micro scale. As an example, consider that the demand is 500 requests per second at 2 different times of the day, but these 500 requests within the second may not arrive uniformly. You may sometimes get a lot of requests at once, and sometimes you may have times where there is a large inter-arrival distance between these requests, and we call these variations micro-scale variations in the demand. Another challenge is how to do just the right amount of scaling according to the user demand. Suppose we want to serve a demand of 45 requests per second using one server and one model variant. Now, suppose we use this model which has a throughput of around 30 requests per second, which means that we do not have enough capacity to serve the 45 requests, and we would actually have to drop the remaining requests, resulting in SLO violations. This means we have actually underscaled the system and we have to drop the requests. Another option would be to use this other model variant, which has a capacity of 55 requests per second, and we can now definitely meet the demand using this model variant, but in fact, we actually had better options which could have served the demand with higher accuracy. So this means that we have actually overscaled the system, resulting in more accuracy degradation than was needed. So in this case, the right amount of accuracy scaling corresponds to this particular model variant, which can just about serve the demand with the minimal degradation in accuracy. Now here I've only shown an example of choosing one model variant for one server using a fixed demand, but in reality, we have to do this on a cluster of heterogeneous servers with many model variants serving many different applications, which makes this quite a complicated problem to solve. So in the context of a cluster, the thing that we first want to decide is which model variants do we actually want to use, and then where do we actually want to host these models. As we may have heterogeneous hardware, placing them on different servers may result in different throughputs, as some hardware may be faster than others. And then finally, when the models are placed, for a given query that's coming into the system, we want to decide for all the different instances that are hosted, which instance do we want to send the query on. This leads us to a large number of potential configurations, and we only want to select the ones that give us the highest throughput with a minimal accuracy drop. So we now present our system Proteus, which solves the challenges that I just described to you. So to solve the first challenge of handling demand variations at different scales, we feature a two-level system design where for the macro scale variation, we periodically adjust the resource allocation of the system at the cluster level. And to handle the micro scale variations, we use a server level adaptive batching algorithm that adjusts the batch size according to the request arrivals. I will now explain the resource allocation and adaptive batching algorithms in more detail. So let us now consider the resource allocation, which corresponds to the challenge of performing the right amount of scaling and adapting to the macro scale variations. So for each of the questions mentioned before, we can actually formulate a sub-problem and then jointly solve these problems together to get an optimal solution. So the first problem can actually be formulated given target query demand. We want to select the model, which we call model selection. The second problem can be formulated as a model placement problem, and the third problem can be formulated as a query assignment problem. We can then jointly solve these subproblems as a mixed integer linear program to get the resource allocation. So we solve this MILP periodically to respond to the macro scale variations. So for the full details of our MILP formulation, please see our paper. I will also now present the adaptive batching algorithm, which executes at the queue of each server independently. So given a server, suppose there are already queue queries in the queue waiting. And then let's say the first query, query one, arrives first and therefore is shown with the lightest color here. Our goal here is to figure out the right batch size that prevents any of the queries in the queue to time out. But we also want the largest batch size as possible to maximize the resource utilization. Suppose that query one is also going to be the first one to time out because it's the first one to arrive. And since DNN inference is highly deterministic, we can actually profile the model variant offline to get its execution time with different batch sizes. So we can actually estimate the total time it would take to execute 2 + 1 queries for this server. By subtracting this time from the timeout deadline, we can get a new time point, which actually indicates the maximum amount of time which we should actually wait to get more queries in the queue. For any queries that arrive after this time, it doesn't make sense to put them in the current batch, because if we do that, then the first request in the queue would expire, and we don't want that. So the key idea here is that if the request arrivals are sparse at any given time, the system will use a smaller batch size and will not wait too long to accumulate more requests in the queue. And if the request arrivals are very dense, it will use a larger batch size and quickly dispatch the batch to improve throughput and minimize SLO violations. All of this is done while ensuring that no request in the queue gets timed out. We implement the above techniques in the Proteus system, whose architecture is shown here. So there are two types of path here, the control path and the data path. The control path is responsible for registering new applications and adjusting the resource allocation in the system. The controller is the component that runs the resource allocation algorithm and then adjusts the resources by loading the models onto the workers and setting up the query routing on the load balancers. The data path is the path taken by the query when it comes in the system to execute. The request first goes from the client to a load balancer, which directs it to the appropriate worker, and the worker appends the request in the adaptive batching queue and then returns the results to the client. So we now show some of our empirical results. We use a fixed size cluster for our experiments. We use 55 different model variants across 9 model families to represent various applications. And to drive load on our system, we used a Twitter trace to represent a real world workload. And we also conducted several experiments with synthetic traces, but for the rest of our evaluation results, please refer to our paper. So we select several baselines. First of all, we chose Clipper, which is a static inference serving system, and we use 2 extreme versions of Clipper, one with the highest accuracy possible and one with the lowest accuracy. We also compared with Sommelier, which is a system that can perform model switching at the server level, but not at the cluster level. And finally, we also compared with a version of InFast that we generated by selecting accuracy to be the objective in InFast to get a 1-to-1 comparison. So compared to the static version of Clipper that uses only the highest accuracy model variant, we can show that the Proteus achieves the highest improvement in terms of throughput and SLO violations. Compared to the high throughput version of Clipper, we get less SLO violations and significantly smaller accuracy drop up to 4x. This is due to the adaptive batching algorithm, which we evaluate in more detail in our paper. We also show that compared to Sommelier and InFast, Proteus drops 2.5x to 3x less accuracy while meeting the demand. And you can also show that Proteus has up to 10 times less SLO violations compared to these approaches. The final thing I want to bring to your attention is to notice that accuracy scaling here, you can see that it starts at about 250 requests per second and goes up to about 1,000 requests per second. This means that using accuracy scaling, we can actually serve about 4 times more requests using the same amount of hardware with some accuracy drop. This means that the provider can actually provision hardware for 4 times less than the peak and still be able to meet the demand variation without needing to provision hardware for the peak. So the key takeaway here is that Proteus advocates accuracy scaling as an alternative approach to hardware scaling. It reduces SLO timeouts by 2 to 10x and accuracy drop by up to 3x compared to state-of-the-art baselines, and it allows us to serve 4 times more requests using the same hardware. Thank you.
Any questions?
Can you elaborate more on how your technique works for autoregressive models? I mean, one example is that for models that requires run the entire neural network multiple times, and can you switch the base model during the middle of the execution, or you have to wait until the end to?
Yeah. So yeah, we don't switch model variants like during the execution. So the model, like we only do like the execution completely finishes, and then we can swap out the model variant. So yeah.
Any other questions? I had one question. In inference model, the accuracy can change from input to input. How do you handle it?
Yeah, so that is actually a good question. That is part of a future work that we're currently exploring, is to look at how the accuracy changes with the input. What we do right now is we actually profile the accuracy of the model offline, and then we assume that if the request goes to that model variant that has like 85% accuracy, then the user is getting 85% accuracy. But yeah, the accuracy can depend on the request, which we are currently exploring right now. Yeah.
All right, let's thank the speaker again. So we have our fourth and final talk given by Xupeng Miao. So he was the first speaker in this session as well. So he'll be talking about SpotServe, which deals with serving generative large language models on preemptible instances. And I think this work won the Distinguished Artifact Award, right? Yep. So with that, let's.
Oh, it works. Oh, hi everyone. Hello everyone. It's Xupeng again. Welcome to our second talk about SpotServe, which is the first large language model serving system on preemptible instance. This work was done by members from CMU Kelly's group, as well as our colleagues from Peking University and the Chinese University of Hong Kong. Many of us in today's talk have introduced language models and their applications. Due to their large scale of model parameters, language models are becoming the foundation of many important tools in our daily life. But one big issue of language model is their price. Serving language models is becoming increasingly expensive, even for these large companies who are providing some language model service APIs. So let's take ChatGPT as an example and explain why serving is expensive. We clarify that one major reason is the hardware resources. For example, if you build your own language model service with open source pre-trained model by using on-demand GPU instance from public clouds, for example, running a 70 billion Llama 2 model needs 4 A100 GPUs, it will lead to very similar economic costs as using ChatGPT service. An alternative solution here are spot instance. Expect on-demand GPU instance. Modern cloud usually provides spot GPU instance, which can be at most 10 times cheaper than on-demand instance. But the problem is this resource might be preempted at any time by the cloud provider. Here we show a real 12-hour trace about spot instance running collected from AWS. On average, preemption happens once every 5 minutes, and in the worst case, it will happen every minute. Our work, SpotServe, is the first language model serving system built on this kind of spot instance that can automatically handle these preemptions. To achieve this target, we propose several innovative contributions, including dynamic reparallelization, efficiently context migration, and stateful inference state recovery. Our system can achieve 2 times economic cost saving and preserve very low time latency at the same time. Now let's move on to some details. So if we want to build language model serving systems on spot instance to save money, we first need to understand what's the fundamental issue when preemption happens during LLM serving. Before illustrating the details, I would like to briefly mention the background knowledge about distributed LLM serving. As mentioned by previous talks, people usually leverage tensor model parallelism and pipeline model parallelism to partition the language model into different GPUs because of the limited GPU memory capacity. There are also some other choices we didn't touch here, like sequence parallelism or sharded data parallelism, but they will not change our motivation and system design. In practice, the model partitioning strategies can be very complex due to their fine-grained combination. So for example, in this case, Suppose we have 4 GPU instances. We first partition the model into 2 pipeline stages, and within each pipeline stage, there will be 2 instances working together using tensor model parallelism. The serving process starts with request R0, and after a few seconds, the first two instances in stage 0 have completed their computation and start to work on the next request. And the other 2 instances in stage 1 are still working on the previous request due to the pipeline data dependency. The decoding process will continue iteratively and until certain timestamp. Suppose the second instance is preempted, what will happen? The first problem is the inference process of request R1 is going to be interrupted. Another big issue here is called chain crashing, because both the data dependencies in pipeline model parallelism and the collective communication operators in tensor model parallelism do not naturally provide any fault tolerance. So the preemption of a single GPU instance can potentially hang all the other instances in the same inference pipeline. Then the affected instance will not be physically terminated, but they will stay idle until new instances are allocated to establish new inference pipelines. After that, the system have to go through some environment reinitialization or reloading model parameters from remote file storage and restarting the interrupted requests. In practice, you may have multiple inference pipelines, and during preemption happens if the overall system throughput decreases to a certain level, which is lower than the request arrival rate, then the request will be stalled, leading to the increasing of their scheduling overheads. So how to handle this interrupted and stalled inference request problem? The opportunity here is modern clouds usually offer us grace period. For example, Google will notify users 30 seconds before the preemption really happens. And AWS also has a 2 minutes grace period. This grace period cannot directly solve this problem, but it provides us a chance to do something proactively. We will show that by using this short time period, we can significantly reduce the preemption effects to inference latency. When preemption happens, a naive approach will block all the other instances due to chain crashing and waste a lot of compute resources. Instead, in SpecInfer here, we managed to change the parallel configuration to fully utilize the alive GPU resources. Note that finding the right parallel configuration is non-trivial because it's related to the trade-offs between inference latency and throughput. For example, pipeline parallelism will selectively increase latency but leads to a very high throughput. On the contrary, tensor model parallelism reduces the latency but also involves some overheads to the throughput. Here, we propose an adaptive optimization algorithm to find the optimal solution in response to both the dynamic spot instance availability and the fluctuating inference workloads. Now, the following question is when and how we should change the parallel configuration. We introduced the context migration mechanism to solve this problem. We may not want the reparallelization happen after preemption, because restarting the whole system or the cluster can be time-consuming. We would like to opportunistically reuse some existing GPU memory contexts rather than destroying them. Here, the contexts include both model parameters and value cache. In particular, we want to migrate this context information among these GPUs to finish the reparallelization process before preemption really happens. Considering the model is partitioned among GPUs, how to decide the migration plan is also a problem. Although we get the new parallel configuration, but for each instance, we still don't know which topology position in the new parallel configuration will be its migration target. Here, we also involve a graph meshing algorithm to achieve efficient configuration transformation. The key idea is to formulate the mapping relationship as a graph, and the migration costs are the weights of edges between original position and the target position. Then we can apply KM algorithm to figure out the optimal migration plan with minimum migration overheads. Another advantage of context migration is that we can easily resume the interrupted request from the migrated value cache. Like in this figure, request R2 will directly start its decoding steps without rerunning previously interrupted results. Combining all these techniques together, we build SpotServe, the first LLM serving system on Spot instance, and we evaluate our system on real traces collected from AWS. In addition, we are also wondering, what if we allow the users to mix the usage of Spot instance with on-demand instance? It's reasonable because sometimes allocating Spot instance from cloud can be difficult. For some latency-sensitive scenarios, you may want to allocate on-demand instance immediately to maintain your service quality. So based on the Spot instance trees, we generate two new traces by allocating on-demand instance when preemption happens. We build two baselines. One is to do reparallelization without reusing any GPU context. And another one is to maintain the parallel configuration and only reroute the interrupted requests to other alive inference pipelines. We evaluate our system and these baselines on various scales of models on both static and dynamic inference workloads. The figures on the left show that SpotServe can reduce the P99 tail latency by up to 9.1 times versus baseline methods. Another figure shows the trade-offs between inference latency and the economic cost for different systems and different traces. The most important finding from our work is that by using SpotServe, you can actually save half of your money spent on GPUs, but still achieves very similar average latency. Now the system was open source and obtained Distinguished Artifact Award this year. Welcome to have a try. Okay, thanks for listening.
Any questions?
Hi, thank you for the great talk. When you are considering the doing the reconfiguration, you want to the reconfiguration finished between the grace period, right?
Yes.
So if it is possible that since you want to achieve this, you may not achieve the optimal parallelism. Then if you consider that the server will continue to run a long time, or whether just just finish the reconfiguration after the grace period and to have a better parallelism is a better choice?
Do you mean that the optimizer may not be aware of the future preemption, so that currently if you change to, for example, a new parallel configuration, it will be easily changed by future preemptions?
No, I just want to say that if you want to, you could take more time to do the reconfiguration and to achieve a better parallelism. The server may stay alive for a long time. You cannot predict. You will not know whether the next stop happens, right? So you may.
I'm not sure I get your question correctly, but in our system, actually, we are aware of the migration overheads when we decide which parallel configuration we want to transform. So different configuration may have different transformation overheads. And but more importantly here is that when you decide your new parallel configuration, the first trade-off is about the latency and throughput. For example, if your availability is pretty low, and your system throughput is even lower than your RAW rate, then you may prefer a higher throughput parallel configuration. So otherwise, you may want to have a pretty low latency configuration. So that will be the first trade-off. Yeah.
Yeah, thank you.
Yeah, thanks. Here.
Any other questions?
Yeah.
Oh.
Thank you. Good talk. And are these techniques specific to LLM servings, or can they be applied to other models?
Yeah, good question. Actually, we are not the first work to run machine learning models on spot instance. Previously, we have seen some papers are work like building some machine learning systems to spot instance, for example, for ResNet or small machine learning models. The problem might be little different because for Lambda model, the first difference is that you need to partition the model onto different shards, and you may require at least tens of GPUs to run even a single model. But for ResNet, you can easily run several model replicas within each GPU. So that's the first difference. A second difference is that for LM serving, we need some inference state, or more specifically, the kernel cache, which is also different from previous or other machine learning workloads. Yeah.
Okay, thanks.
Thanks.
You mean the model size and the KV cache?
Yeah, exactly. Yeah.
Okay, thank you.
You have time for one final question, if there's any. All right, so with that, let's thank the speaker again, and this concludes the session.